Okay, let's get started with some announcements first. Okay. All right, how many people have finished Project Zero? Great, so Project Zero is due tomorrow at 5 p.m. Projects will be due at 5 p.m. on Fridays. Projects do allow slip days. Slip days go 5 p.m. to 5 p.m. Homework 1 is live. It's due Wednesday the 11th. Homeworks are going to be due at the last moment of that day, so 11:59 p.m. Those don't have slip days because you're going to use the answers in section the very next day. So no slip days for homeworks. But they'll be every week, and they're pretty short. Projects and homeworks, you can submit them and check them and auto-grade them as many times as you want. The grade you get will be the last thing you submit. So feel free to kind of submit once or 1,000 times. It's all the same. Sections. Okay, so sections are starting. You can go to any, but have priority in your own. If you want, you can go to many. If you love section, that's fine too. In general, most people stayed within the 35 max, but if you'll notice on our poll, there are a couple sections that are oversubscribed. So we're extracting out who was polled in what order, and we're going to send out some email if you're beyond the 35. It doesn't mean you can't go to that section. In fact, you almost certainly can go to whatever section you want, except maybe one section may overfill. However, especially in the first couple weeks when section attendance is particularly high, we want to make sure everybody's got a confirmed seat somewhere. So if you get that email, just go in and change your preference in the poll. There is a survey up. There's a link on Piazza. Please use that survey to enter your preferences and conflicts for the 2 midterms and the final. In general, we'll try to respect preferences, but really we're going to first make sure that there's a solution for all of the conflicts. And typically those conflicts are serious conflicts like class to class, midterm collisions, things like that. So please fill those out so that we know what you prefer and what we have to do in order to make sure everybody can take the exams. Any administrative questions before we move on? Yes?
Can you just explain the slip days real quickly?
Okay, slip days. How do slip days work? You have a budget of slip days. You have 5 slip days, and you can use them without checking with us at any time. You just turn your project in late. You can use up to 2 slip days per project. If you need to use more than 2 per project, email the staff list and check with us, because the edX system more or less allows 2 and then cuts everything off. If you have some serious reason, we'll work it out, but we'll have to work outside of the infrastructure. Yep.
Are they discrete days or can you split them up hourly?
They are slip days, not slip seconds. We measure them in days, and I don't recommend you using a slip day so that you can turn it in at 5:05 p.m. Though you can. Your slip days, do what you want. Any other questions? Yes?
I'm turning my Project Zero on PDX, but how can I know it is being turned in?
How do you know that it's been turned in? Look at the grade book there and make sure that it's kind of shown up. It's also, as you go on, you'll be more familiar with the grading system.
Oh, when I registered for PDX, it only asked for the email address. I didn't put any of my students.
Right. At some point, okay. The question is basically how do we do the joining between your student ID and your edX account?
Yes.
We haven't done it yet, but we will. Don't worry. We have this grand plan where at the end you get grades. It's all going to be good. But for now, it's your account. Any other questions? All right. Oh, one other thing. So if you log in, so I know lots of people check Piazza all the time. Piazza, we're trying our best to make sure there's posts to webcasts when they're available. You can follow those to get push notification. And also lecture slides. By the way, lecture slides have been and will be available before class. But the best place to get these things is on the edX syllabus page. We have a bunch of versions of the slides and 2 versions of the videos. You'll see actually there's already a webcast for today. You wonder how we do that. And the answer is what we have is for the first about half of the class, we've got webcasts from last year that are same topics, and they've been pretty highly edited. So they'll be available a little earlier. And one of the things we're going to want to know at the end is, did you prefer the edited versions, or did you prefer seeing the kind of full, raw experience? Okay, so feel free to check those out and let us know which ones work best for you. All right. Today we're going to talk about informed search. We're going to take what we did last time, thinking about how to define a search problem and how to start with a search tree and explore into the tree in a way that finds your goals. But now we're going to start thinking about how to inject a little bit of information about the specific problem you're solving so that the search algorithm doesn't just kind of blindly push from the top of the tree downward, outward in all directions, and waste a lot of time exploring plans that are unlikely to be successful. So in particular, what we're going to do today is we're going to define a couple of the key ingredients in informed search. We're going to talk about the notion of a heuristic, and you all have already know the word heuristic, but it means something a little different here. There's a very precise technical meaning in the context of informed search, so we're going to define heuristics, and we're going to think about how to develop them. We're going to talk about an algorithm called greedy search, which is the obvious way to use a heuristic, and then we're going to talk about A-star search, which is the good way to use a heuristic. A-star search is kind of the pinnacle of our search unit. Then, at the end of the lecture today, we're going to go back and make one small change in terms of kind of the code to these search algorithms that will have a big payoff in efficiency that's going to prevent us from doing repeated work. And it's an easy change, but it's also a little bit tricky to make sure you do it in a way that doesn't break things. So first we're going to talk about all the search methods, then go and make everything more efficient with graph search. So first let me recap what we mean by a search problem. Okay, a search problem formally, you think about this like an object. What methods does it have? Okay, a search problem has states which represent abstracted configurations of the world. These are things like XY coordinates or bit vectors of where the dots are or where you are in Romania, that kind of thing. They have actions and costs on those actions. And those form a successor function. The successor function models the dynamics of the world. That is, from each state, what happens if you take the actions. There's a start state that says where you are now, and a goal test that tells you what states satisfy your search. And that may just be a single goal state, or it may be a set of states. We had a notion of a search tree, and we're going to see more search trees in a second. In a search tree, there were nodes, and these nodes represented not just a state, but a plan for reaching that state. Okay, so we drew these as kind of a node in a tree. In terms of implementation, usually they're a state with a back pointer, right? But in any case, they represent a plan for reaching a state. So the same state may appear multiple times in the tree if there are multiple ways to achieve it. Plans have costs, and the cost of a plan is the sum of all the action costs that are in it. Right, so an action may be cheap, but if you take a bunch of them, those costs add up, and the thing we care about is the total of all of the costs inside a plan. We also talk about search algorithms. Search algorithms kind of systematically build a search tree from the start state downward, which essentially means thinking about what could happen if you took various actions, and the search tree represents possible futures. The key difference between all the algorithms we saw so far and all the algorithms we're going to see today is what order you choose to explore downward in that tree. We also have this notion of optimality, which means when my algorithm returns a path, that is, when it returns a way of achieving a goal, does it return the one of lowest cost? And we talked about how depth first search and breadth first search were for general costs not optimal, but uniform cost search was. And that's where we ended. Let's quickly remind ourselves what search problems look like. And in particular, it's very tempting to think they're all about walking around in a maze, right? Pac-Man's in a maze, dots are in a maze. You might think it's all mazes. It's not. So here's a problem that really has more to do with pancakes. So imagine you have a stack of pancakes and you're a robo-chef. And your job is to get the big pancake on the bottom, the little pancake on the top, and everything ordered nicely. And your only operation is that you can put your spatula between two pancakes in the stack and flip. And flip kind of reverses the order of the prefix of pancakes above you. So from this position, you could stick your spatula in the middle and flip the top two, and you'd end up with this configuration of pancakes. Right? Maybe that's a little better. Okay, or you could flip the top three, and now you have this beautiful stack. And in fact, we're going to consider this to be the solution. Right? So the goal test is going to say the pancakes are in this decreasing order. Or you could flip everything, and now you're kind of where you started, but upside down. Okay, so these are your actions. These are your states. These states, when we actually implement them, how would we do this? Well, we wouldn't draw little pancakes. Obviously, we'd have some like tuple that's a permutation of the numbers or something like that. So in memory, this thing might be a permutation of integers, but conceptually, it's a configuration of pancakes. And these are the actions you can take. Now there might be costs as well, so if you're a robot and you really want to kind of conserve power, maybe it's harder to flip more pancakes. We might say the cost is the number of pancakes flipped. Or maybe it's not, maybe all you care about is time and the cost is 1 no matter how many things you flip. Those are different variants of the search problem. So for now we're going to say the cost is the number flipped. Now, who cares about this? Well, you might have a robo-chef that deeply cares about this. You would be surprised who cares about this pancake problem. In particular, probably the last 2 people you would be expecting to write a paper about it together, which is Bill Gates and Christos Papadimitriou. But there you go. What do these people have in common? Bill Gates, Christos Papadimitriou, pancake flipping robots, whatever. Okay, moving on. This is the state graph corresponding to this search problem. And you can see there are a bunch of configurations of the pancake, and for this small instance, there aren't that many, right? And you can see that all of the arcs here, they're bidirectional because you can undo what you did just for this particular search problem, not for all. And they have various numbers on them that indicate their weights. Now, one of these here is the solution state. So in particular, the goal test only returns true here. And where's your start state? Who knows where your start state is, right? Each start state would be a different instance of the problem. All right, so that's the graph. And now what is the search tree and the search algorithm? Well, we had this generic pseudocode. I'm not going to walk you through the pseudocode, though. It's in the slides and it's in the book. The basic idea of this search, however, is that you maintain a list of candidate plans. These plans all do something, but you're not sure which one you're going to do. So you maintain a list of things you might do, right? And at the beginning, that list is just, I am at the start and I haven't done anything. And the cycle of tree search is you take something off of this set. The set is called the fringe, right? You take something off the set, you check to see if it's a goal, and if it's not, you expand it, meaning you extend it by 1 action, and you put the new extensions onto the fringe. Onto the fringe, if you want them cold, you put them in the fridge. Okay, too much pancakes. Anyway, so when I pop this off, what goes onto the fringe? I look at it, it's not a goal, so I put its children, which are these 3 other states, onto the fringe. Now this is my fringe, and when I compute these nodes on the fringe, I have to kind of keep track of the state, a back pointer that lets me reconstruct the path to the root, and the costs. And in general, the actions have a cost, and so I'm going to add these up to compute cumulative costs. All right, so this is my new fringe. I now have 3 things on my fringe. I'm going to pop something off. Maybe it's this leftmost thing. Its children go on the fringe. And then maybe I pop the rightmost thing. Its children go on the fringe. And I keep doing this until I pop something off of the fringe that passes the goal test. That's going to be this guy over here, maybe. And this represents a particular plan, which is flip 4, then flip 3. It has a total or cumulative cost of 7. Right? This is a very important idea of cumulative costs. This one has cumulative cost of 7. And if this is the next one that I pop out, then the rules of tree search say as soon as you pop or dequeue a plan that achieves the goal, you return it and you declare victory. So I would return this one maybe and declare victory. That's tree search. Any questions on that? Okay. Now, we talked about a lot of kinds of search. We talked about depth first search and breadth first search, and then there's uniform cost search, and you can already tell greedy and A* are coming. You've got this whole armada of search algorithms, and it turns out they're basically all the same algorithm. They differ in one place, and if you imagine that there's just a fringe, and there's some method of getting things off of the fringe, and in particular, if you imagine every node on the fringe has a priority, and you always take the thing of best priority, then the data structure you would use for the fringe would be in general a priority queue. And all of these algorithms are just different choices of priority. In depth first search, you want the deepest thing, right? So the best priority might be the negative depth. Breadth first search, it might be the depth. So lowest depth is the shallowest thing. In uniform cost search, it would be the cumulative cost. And we're going to see different search algorithms now. But conceptually, it's just a matter of choosing what comes off the fringe. And even for implementation, you can build one search algorithm and just pass in different mappings from nodes to real values. Okay. Now in practice, there's an extra log n overhead for using a priority queue. So when you learn depth first search and breadth first search in previous classes, you just use queues and stacks, which give you that same behavior without having the log n overhead. So there are special cases and special data structures, but conceptually, there's just kind of one master data structure called a priority queue. Let's recap the important bit of uninformed search so that we can fix it, right? we talked about an algorithm called Uniform Cost Search. And remember, all tree searches, they all have a bunch of partial plans on the queue, and you look at them all and you take something next. Depth first search takes a deepest one next. Uniform Cost Search, the rule was, of all of these plans, take the one of lowest cumulative cost. And then you put its children on, and its children generally cost more, so maybe you kind of now go over to somewhere else that's still cheap. And so in general, the behavior is you explore kind of from the top downward in a relatively uniform way, like breadth first search, but it's not uniform in terms of tiers of the tree, right? It's not everything of one action, then two action, then three action. It's uniform in cost. You do basically everything that costs about 1, then everything that costs about 2, and the shape of that may be more or less flat based on how uniform the costs are across the problem. So this was good. I can show you a demo of what it does. It's good because it's complete, right? You're being methodical in a way that makes sure you will get to a solution, and it's optimal. The first thing you find, because you're going from cheapest, you're kind of looking at all the cheap plans first. And since you're checking all the cheap plans first, you're going to find the cheapest of the goals first. So let's look at a demo of this. All right, so what does this show? This shows, this is a visualization. This is also in your project ones. This is a visualization of the Pac-Man agent. This is for solving the pathing problem, which is one of many problems you could solve in the Pac-Man domain. This is for getting to that dot. And so the colors indicate for each state, which is an XY coordinate here, the redder it is, the earlier it was discovered in the process of the algorithm. So you first find ways to get nearby, and then it takes longer to find ways to get to the corners. And one of the last things you find is the way to get to the lower left corner, and kind of at the same time you basically find the ways to get the upper right corner and so on. Okay, so you can see that it explored all of the things you could do in any direction until it hit this dot, and at that point it had looked at every plan that's that expensive, which also gets you in all kinds of crazy other directions. All right. So the bad there, kind of conceptually, is that you explore in every direction, right? And the reason you do that is because you have no information about where the goal is. So let's try to fix that. Let's think about something called informed search. And in informed search, rather than just having this notion that you have a tree and you're going to work your way downward, and you don't know anything about this tree until you get successors and costs back, right? In informed search, you have some indicator of where the goal is, right? And that lets you focus your work in directions that make progress. In particular, we're going to have something called a heuristic. A heuristic is not what pops into your head when you think about the common notion of a heuristic. The common notion of a heuristic, like a rule of thumb, is about an action. I'm in this situation. What should I do? And the thing that makes it a heuristic in kind of the generic notion of heuristic here is that it's kind of, it may not be the right thing, but it's often the right thing. Our technical notion of heuristic in search is very different. Our heuristic is a function. It maps states to real numbers. It says nothing about actions. It maps states to real numbers, and it estimates how close you are to a goal. So it's less like a rule of thumb, and it's more like a little goal detector that beeps more loudly as you get closer to the goal, right? The search algorithm is responsible for figuring out what to do with that information. A heuristic just tells you whether it's hot or cold. Okay. Your heuristic is designed for your problem. There's only one uniform cost search. Once you build it, you're done. Each problem is going to have a different heuristic because each problem has a different kind of domain structure that lets you build good heuristics. So here's what a heuristic might look like. Your search algorithm is now bolted onto a goodness of where I am detector. And you can think about this like hot, cold. So if you're far away, it says you're far. If you get closer, it starts to say you're closer. And when you're at the goal, it tells you you're at the goal. All right, so let's think about what a heuristic might be. All right, it's very hard to think about from a position like this whether Pac-Man should move left or right, right? That's what search does. However, we can think about how close we are to the goal without thinking about where the walls are or how I should get there. So how many steps away is the goal? Well, I mean, I don't know, right? I mean, you kind of have to solve the problem to figure that out for real to take into account the walls. But if all I want is an estimate of how close I am, what might I say? Like, what's a reasonable number of steps away here? How could I compute something? You could look like Manhattan distance, right? I mean, we could be way farther than that based on the maze structure, but if we computed the Manhattan distance, then that would look something like this. We'd say maybe Manhattan distance is 10 plus 5. That's the x absolute value plus the y absolute value. Could we be any closer than that? No, right? Even if the walls all vanish, we're no closer than that, we might be a lot farther. So it's an estimate. In this case, it's an underestimate of the distance. We could use Euclidean distance too, right? There's no way to get there faster than 11.2. In fact, in this case, and since you can't move on diagonals, you can't even achieve that even with a totally empty maze, but that's also a heuristic. A heuristic is any mapping from states to numbers. Obviously, it's better if it actually gives you something like the right answer. Okay, remember our problem trying to drive from Arad to Bucharest, and we had streets and distances associated with them? Well, a heuristic for mapping here in this case might be something like the straight line distance, and that's what's shown here in this box h of x. So this h of x is literally a mapping from states to numbers, right? States on one side, numbers on the other, and for each city, it shows you how far away you are in the straight line distance. So you can see in here, Bucharest is 0 because you're at your goal, and Arad, which is pretty far away, is 366. So it tells you whether you're getting closer. We'll have to see how that helps, but that's a heuristic. Here's another heuristic, right? Here's my pancakes. Now you might look at this and be like, if somebody showed you this pancake configuration here and said, how far away are you? Like, I don't know. This is a case where it's not so obvious how to come up with a heuristic, but you can still do it. So, for example, I might say the number of the largest pancake that's out of place. Well, how am I going to get that pancake in place? It kind of has to be at the top, and I have to flip it, right? It may or may not be at the top, but at some point it will be, and then I'll flip it, and it's going to cost the size of the pancake. So in this case, we've come up with a heuristic. It assigns a number everywhere, and you can see that as I get closer to the goal, it gets smaller, but this one's not super informative. There are big stretches of the state space that are all called 4, right? But there's a heuristic, mapping from states to numbers. What do we do with a mapping from states to numbers? Well, it doesn't tell you what action to take, but it's pretty easy to incorporate it into what's called a greedy search. Now, we're going to talk about something later in the class that's called a local search, where, for example, you just look at your actions, you see which one improves the heuristic, and then you take it. Like in the real world, you actually take it even if now there's no way to solve it. Greedy search is not local search. We're still going to have a fringe. We're still going to be able to backtrack. The only difference in greedy search is that the priority has something to do with the heuristic. So let's say I was in this map and I was at Arad, which remember is here, and I want to get here. How could I use the heuristic? Well, I could look at the things around me, right? And it seems like to the extent that I'm going to explore one of the children of this state, it should probably be this one. And the heuristic can tell you that. So greedy search is simple. It's a tree search. And what you do is you expand a node that seems closest, which formally means you choose amongst the nodes on the fringe, you choose the one with lowest heuristic value. So heuristics aren't cumulative. They're just numbers. They're one-shot answers about where you are and where the goal is. So here we have a rod on the fringe. It's some distance away, and it's our only choice, so we expand it. So then 3 other plans are now on my fringe, right? The one where I go straight to Sibiu, which is here. The one where I go straight to Timișoara, which is here. And one where I go to Zurich, right? And you can see that according to the heuristic, Sibiu makes the most progress. So with these 3 things on the fringe, what greedy search is going to do next is expand Sibiu, right? The other ones stay on the fringe. We might need them later. We just don't expand them now. So off they come, and now you can see that all the places you can get to from Sibiu, including going back to Arad, right? That is a different node in the tree because there's a difference between the plan where I'm just at Arad and I haven't done anything and the plan where I go to Sibiu and back, right? So all of these things are on the fringe, and which one is closest? Before we look at what it's going to do, let's actually stare at Romania for a second. Oh, that was unexpected. Okay. Let's stare at Romania. So how are we going to get from here to here? Well, it seems to make sense we're going to go through here. And then there's a high road that goes in 2 steps through Fagaras. And then there's a low road that in 3 steps goes through some cities I can't pronounce. Okay, and you can't, these are small numbers, but which one is the actual optimal path? The low road, right? Because even though there are 3 arcs, they add up to a smaller number. So an optimal search would choose the low road. What would breadth first search choose? It's going to return the high road. It's going to find the shallowest in terms of number of steps, So it's going to return the high road. But, breadth first search is not on our plate right now, it's greedy. So we've got this, and the question is whether it's going to take the high road or whether it's going to take the low road. In this case, the low road is the optimal one. So in this case, we see Fagaras, which is on the high road, is closer than this city I cannot pronounce, right? In particular, the heuristics say, if you had to choose, then first explore Fagaras. So we pop that off and we look at its children. Look what's on the fringe. All this stuff is on the fringe, right? Right? And what's cheapest? Well, Bucharest. So we pop it off and we're done. Good idea. Take things off in order of the heuristic. What could possibly go wrong? Well, yeah, that can go wrong. What just happened can go wrong. You can get a path that's not optimal, right? Because you took what at every step looked to be closest, and then you got to a goal, and you didn't go back and check the other options, right? There is a good path through here, but once you're standing right next to Bucharest in your simulation, you just keep on with it. Okay, so what can go wrong? You might be suboptimal. In particular, if you looked at this, does this look more like a depth-first search or a breadth-first search? It's a lot more like a depth-first search, so keep that in mind, right? Essentially, as you get deeper, the heuristic values tend to get smaller because you're going closer to the goal, and so you tend to keep exploring things, and then they tend to keep getting smaller. So this tends to be kind of like a guided depth-first search. All right, this can go wrong. You can find a goal, and it can be issued. Okay. So this strategy formally is of everything on the queue, expand a node that you think is closest to the goal state. Formally, that's the one where the heuristic value is smallest. And a common case is it takes you straight to a goal that isn't actually the optimal goal. There's no guarantee that it's going to take you to a goal or that it'll be suboptimal. But a common thing you can have in your head as a caricature is that it's typically going to take you to some suboptimal goal. Quickly. Is there a question? Yep. Oh, you mean how you know that your heuristic tells you that sub u is 253 away? That is up to whoever handed you this list. That person hopefully knew something about Romania, and if they made a mistake, that's not your problem, right? So it's good to think that we wear two hats. One hat is when we formulate a problem and we think hard about Bucharest and hard about Romania, and we look at the maps and we come up with a heuristic. We're formulating problems. We have to know a lot about Romania. Then there's the one where we say, I'm a search algorithm. You gave me a search, your start state and a successor function and a heuristic. I don't know what these numbers mean. I hope they're real, right? So yeah. Other questions? Yep.
But then, doesn't the optimal path pop up naturally while you make the heuristic estimates? Like, if you have an algorithm that gives you heuristic estimates of what the shortest path is, can't you just use the heuristics right off the bat?
So the question is, somehow didn't you know the optimal path to get the heuristic? The heuristic isn't the distance to the goal. That would require knowing the optimal path. The heuristic is something like the Euclidean distance in Pac-Man that you can compute without knowing what the walls do or without knowing where the roads are in Romania. You just look at GPS coordinates and say, if I could drill through the earth, here's how close I am. Right? So in general, no. The whole point is the heuristic doesn't know the solution. We'll come back to this issue. It's a good question. Okay, so a common case, straight to the wrong goal with best first search. And the worst case is kind of like a badly guided depth first search. The heuristic tells you what to do next. You saw what breadth first search can do when it goes kind of off the rails. It can kind of explore all kinds of weird stuff. And that can happen too. So in the search tree, you could explore not just straight down to a goal, you could explore everywhere else. The heuristic could be adversarial. It could tell you to look everywhere except where the goals are. Probably that's not going to happen. No one's going to design that, especially since it's usually you doing the designing. But in principle, in terms of kind of theoretic what you can show, if you don't know anything about the heuristic, kind of anything could happen. It's just like depth first search. Let's look at this thing in action. Okay. All right. So here's greedy. Let's look at what we're seeing here. This shows every state that's not black is one that was expanded before a solution was found. The red ones were expanded first. And this makes sense because greedy has the option, right? It can expand going left or going right, and going left brings you closer, so it expands that. And then it keeps expanding things that are getting closer to the goal, and it keeps expanding, if you can see my pointer here. And then at some point it expands this one. There's no children, and now the closest thing on the fringe to the goal is over here. And so it starts expanding those, and it kind of follows now to the goal. So it didn't get stuck in the corner in some sense. It did have backup options. It did eventually get a path from from its backup list on the fringe. But that path, which path did it get? Well, it got this one where you go left. What's the optimal thing to do from the start? Yeah, you should go right. Greedy doesn't like things like that, right? Why doesn't greedy like to go right? Why would you explore something that the only thing you know about is the heuristic, and the only thing the heuristic is telling you is that this is worse than the other option? You're just not going to do it. And since you found a path on the other tree, you don't come back and check what might have been, right? So that's the problem. Greedy goes kind of straight in the wrong direction. So our challenge now is to take all of this and put it together. Our challenge is to take everything we know about heuristics, which tell you whether or not you're close, but somehow not lose this idea of uniform cost search where you explore out in other directions in case they might turn out to be optimal. Okay, so we need to somehow both head towards the goal and hedge our bets. Anything that we don't know is a bad path, we should pursue it. Okay, so how's this going to work? Let me tell you a parable. Have you heard of the story of the tortoise and the hare? Raise your hand if you know the tortoise and the hare. Okay, this will go well. The tortoise, let's imagine this story is really not about the tortoise and the hare. This story is really about uniform cost search and greedy search. So who is the tortoise? The tortoise is uniform cost search. What does the tortoise / uniform cost search do? It tries methodically every possible plan that doesn't cost too much. It tries all the things you might do, and eventually it finally finds a plan at a certain cost that achieves your goal. Right? Slow, steady, it eventually does the right thing. That is uniform cost search. The hare is greedy search. Okay, so what does the hare / greedy search do? It like zips along towards wherever the heuristic says the goal is, and at some point it maybe gets lost and eats some carrots. Okay? So we want to be able to put these things together. Okay, I don't remember how the original parable ended, but in this class, the way this parable ends is we're going to combine these things to form this. Okay. This thing is A* search. Like the tortoise, it's going to slowly and methodically check everything that might be optimal. But because it's got the heuristic sitting on its back, it's going to be able to prove that some things that live in the totally wrong direction are guaranteed to be suboptimal, even though it hasn't gone very far in that direction. So somehow the heuristic is going to serve as a bound that tells it what things uniform cost search doesn't have to bother with. That's the combination that we're looking for. So let's figure out how exactly you bolt together a tortoise and a hare. Here's an example graph. And let's see how we're going to bolt these things together. So let's actually, for this one, let's run the first thing. Let's run uniform cost search directly. So what does uniform cost search do? It orders its options, its expansion options, by path cost. That's cumulative path cost. This is also called the backward cost because from a state or a node, it represents the cost all the way back to the start. It has to do with not just where you are, but how much it costs to get there. That's the backward cost. That's called G of n. It's not particularly easy to remember, but G of n is the backward cost or the cumulative cost of the actions. So what's uniform cost search do? Let's do a quick uniform cost search in the corner. Uniform cost search is going to say, all right, what's on my queue? The path S, which has cumulative cost 0. That's the only thing I can dequeue, so I pop it. Now I have the only successor, which is S to A, which has cumulative cost 1. It's my only choice, so I expand it. And now I have S to A to E, which would have cumulative cost 9. It has S to A to B, which has cumulative cost 2. And so what do? We do S to A to B because we're doing all the cheap things, right? So what? Oh yeah, there was D in there too. S to A to D that costs 4. Okay, well, good. We didn't do that. S to A to B costs 2. Then there's S to A to B to C, which costs 3. So you can see what's happening. We're doing all of the cheap stuff first, right? Eventually, we're going to find the optimal thing, right? Because all of these cheap things, which are basically down here, all of these things don't actually lead to the goal, and we'll eventually start down the S to A to D path. We'll eventually find the optimal goal. And which is the optimal path here? It's the one S to A to D to G that goes kind of straight to the right on the slide. So uniform cost search spends a lot of time trying everything that's cheap, even though the heuristic is screaming as loud as it can, like, turn back. You are making yourself farther from the goal, and this plan is getting expensive because you're doing stuff. So all of your signs tell you to turn back, but uniform cost search says, no, it's still cheap. There is still hope, right? Greedy orders not by the cumulative cost of actions, the backward cost, but by something called the forward cost, which is the heuristic. Right? It's forward because it says something about how much cost there is between where you are and the goal, which is forward of you. Right? That's in your future. So greedy, what does greedy explore? Well, it starts with S to A, and then when it gets to the point where it's got, where it's going to have S to A to E with cost, well, it'll have S to A to E, S to A to D. That's definitely not a D. S to A to D, S to A to B, and where S to A to B was cheap for uniform cost search, now we go by the heuristic. S to A to E costs 1, because we're like right there. S to A to D costs 2, and S to A to B costs 6. So when you're just listening to the heuristic, B looks terrible, and it says, E, we're almost there, go, 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 right? Even though we just spent 8 to get there, which means we probably don't want this plan in the end, right? We don't care about what's kind of past. All we care about is what's in the future. So what will greedy do? It'll zip straight to the wrong goal, which is kind of its caricature. All right, so what should A star, this thing where we bolt them together? How do you bolt together two numbers? We add them. Okay, so that's all it is. We add the numbers. Okay, there we go. Okay. A star search is just like these other algorithms, except you order by the sum of your backward cost, which you get by adding up the arcs as you take them, and your forward cost, which comes out of your heuristic function. Your heuristic's a black box. You put in a state, out pops a real number. You don't know what's going on in there. Okay, so what's going to happen here? What's going to happen here is you're going to kind of work through it, and what will happen is you'll go kind of to the correct goal, because as soon as you see the cost of 8 in your G, you're going to say, okay, this path to E is bad. And as soon as you see H saying turn back, you're going to say, okay, going through B is bad, and you're going to continue down the correct path. So we're going to work through some other examples. I won't work through this one right now, though I actually encourage you to work through this graph on your own. I think it's a really useful small graph. Okay, so that's it. We add together the cumulative costs, which tell you how much this plan has cost so far, plus the heuristic, which tells you how much it's going to cost to get to the end. Altogether, that's kind of an estimate of the whole health of this path, and we want to take paths that are good both in their past and their future. Okay. Great. So let's run A star search on some small examples where surely it will do the right thing. So let's do a mini A star search. We start with S, which has, well, A star search uses the sum of path cost and heuristic, which means S costs what? It's going to cost 0 plus 3, so its priority will be 3. So that one comes off. On goes S to A and S to B. What is S to A's F cost? Well, S to A has a cumulative cost of 2 and a heuristic cost of 2, so it costs 4. S to B has a cumulative cost of 2 and a heuristic of 1, so it costs 3. So we head down the S to B path, which is, reasonable enough. The heuristic's saying it's better. All right, so we pop that off. Now we have S to B to G. S to B to G has cumulative cost of 5 and heuristic of 0. And so its total cost is 5. Now, if I just return this and said, I found a path that reaches the goal, here it is, I would return a path that costs 5. Is that optimal? No. Fortunately, if you read the fine print in the algorithm, you don't stop when you in-queue a goal. You stop when you de-queue a goal. And now you can see why. Because S to A still looks better than this SBG path, right? It's still there on the queue. It's still saying pick me, pick me. And so if we leave S to B to G on the queue, we'll pop off S to A. We'll put on S to A to G, which will have a cumulative cost of 4, a heuristic of 0, a cost of 4. And now when we dequeue the next cheapest thing on F cost, we dequeue the optimal goal, we get the right answer, we avert disaster, everything's good. Okay? So the short answer is you don't stop when you in-queue a goal. You stop when you dequeue a goal. The goal test happens when you dequeue. Yes?
Is A star always guaranteed to return the optimal solution?
Is A star always guaranteed to be optimal? Yes, subject to some fine print. We're going to spend a lot of time talking about the fine print, though.
Professor,
Yes?
can you explain again what you mean by NQ and DQ?
Okay, so remember the question was, what's the difference between NQ and DQ? What do I mean by that? Remember the fundamental cycle is there's a fringe, and what you do is you pull things off the fringe, that's called dequeuing. You expand them, and you take their children and put them on the fringe. That's called NQing. Yes?
So if the H for A in this one was, say, 4 or something, then it would return the goal of 5, even though 4 would be cheaper.
Great. You've, hold that question. What happens if A has a high heuristic? Great, that was a perfect question. In fact, it's my next slide. So I'll let you finish your question if this slide doesn't answer it. Okay, I'm going to do this slide, and then I'm going to answer his question, and then I'm going to answer your question. All right, so let's do A star and see whether or not it is optimal. After all, it is this pinnacle of, turtle-rabbit combination. We should be able to get something optimal out of it. So let's run it. Okay, so we start with S. That has cumulative cost of 0, H of 7, so it's got a priority of 7. We take that off. What do we NQ? S to A, which has cumulative cost of 1 and H of 6, so it's got a cost of 7 as well. We get S to G, right? Okay, but that's fine because it's just going on the queue. It has cost of 5 plus heuristic of 0, so it has a cost of 5. And now we pop off the cheapest thing, which is S to G. We return it, and we've just returned this path S to G, which is not optimal. So, is A star search optimal? Apparently not. Can your heuristic mess you up? Apparently. Should we all be depressed? Maybe. Okay. But something particular went wrong here. Let's look at what went wrong. Let me first come back to these questions. Did this answer the question down here? Do you have a new question?
Well, no, I had an answer.
Okay, questions first, then answers. Does this answer your question as well?
Yeah, I was just going to ask whether the term A star comes from.
Where the name A star comes from, the star means optimal, and this is a paper that had multiple algorithms. It's like the worst. It's the worst naming ever. The only thing that's worse is when we talk about the AC3 algorithm, and you ask me about whatever happened to AC1 and 2, right? It's not a good name, but it's a famous algorithm and it stuck. But the star means optimal. Okay. So what went wrong? There's an answer of what went wrong. What went wrong?
The heuristic for A was an overestimate.
Yeah, so the problem here is, what the problem is the 7, right? S to A is the thing we should explore, but look, it costs 7. It's terrible. We should go with S to G. And the thing is, we need to make sure that things like S to A, which actually might still turn out to be the solution, that they're going to be cheaper than S to G at a cost of 5. So H has to be smaller than this, right? And in particular, what we need is that H, which estimates the future cost, it needs to be a lower bound, right? And if it's a lower bound, what this means is we gradually replace this lower bound with real costs, and sometimes the bound is good enough that we can skip computation. Okay, but if we just put random arbitrary numbers here, yeah, no, optimality, efficiency, it's gonna be a mess. All right, so what went wrong here was the actual bad goal cost, the 5, was worse than the estimated good goal cost, which is the 7. And so that kind of tells you what H could possibly be and avoid disaster. And we need in general estimates to be less than actual costs. So let's talk about admissibility, which is this formal notion of what it means to be a lower bound. Okay. So the idea about admissibility is if you have an inadmissible, and when you see inadmissible, you should think pessimistic, or at least sometimes pessimistic. An inadmissible heuristics, they break your optimality by taking good plans like that S to A to G plan or on the high road, and they trap them on the fringe by making them look bad. The thing that makes the plan, even though so far it's cheap, the thing that makes it look bad is that its future is like gloom and doom. So that's why you can't be pessimistic about your future. An admissible, and you should read admissible as optimistic, an optimistic heuristic can slow down a bad plan by saying, I don't know how bad this is, but it's at least this bad, and if that doesn't sound good to you, go search somewhere else. So when it's optimistic, you slow down the bad plans, but never in a way that prevents you from processing the true costs in an optimal way. So formally, we take a heuristic H, which remember maps states to real numbers, and we say it's admissible or optimistic if it's less than H star. What's H star? H star is a mathematical way of writing the true cost to the nearest goal to that state. Okay, so your heuristic has to be less than this magical heuristic that always returns the actual distance to the goal. And it has to be positive if you want things to work out. In particular, that means it's got to be what at a goal? It's got to be 0, because it's got to be positive, it's got to be less than the true cost. So we now know a lot about admissible heuristics. So H star here is the true cost to a nearest goal. Let's see some examples. Remember Pac-Man, we talked about Manhattan distance, and the Manhattan distance from Pac-Man to the dot might be 15. Is that admissible? Is the Manhattan distance always closer than whatever you get when you make your way through the maze? Yes? No? Admissible? Seems reasonable. How would I show it's admissible? Okay, well, we'll come back to that in a second. Remember here, we said it's a cost 4 because the pancake number 4 is out of place. And if I flip this, it costs 4. But I kind of have to flip it and then flip again. It actually costs 7. So it's an underestimate. That means it's admissible. But how do I prove that something's admissible? There are multiple techniques. In general, coming up with a heuristic that's going to be admissible is most of what's involved in using A star practically. Now in this case, the easiest way to show these things are admissible is to construct, so for the case of the Manhattan distance, let's construct this notion of a relaxed problem. So one argument I can make, we'll come back to this notion of relaxed problems. One argument I can make is, well, what is the true path, the optimal way of getting to the dot? I don't know, it's something that goes through the maze. What if I took the maze and I removed all the walls? I gave Pac-Man the ability to walk through walls. Well, could I have made the problem any harder? Could I have made the goal any further? No, you can still do what you could do before, but now you can also walk through walls. So this new problem, things are only closer than they were in the old problem. And in the new problem, without even running search, it's obvious that the solution is Manhattan. So one way to prove things is to say it's equivalent to some other problem that's easier. Another way is to just make a direct argument, like we did for the pancakes. Like you got to get that number 4 in place. It can only come into place by being at the top of the stack. It's going to cost 4. Maybe you'll do other things. So sometimes you make a direct argument. Sometimes you do something that looks a lot like a reduction. All right. How about this? Let's take our break now. Then we're going to look at a proof that A star tree search is optimal. Then we'll talk about how to make good heuristics, and we'll talk about this change called graph search that just makes everything better. So 2 minutes or so, stand up, stretch out. Okay, let's, what we're going to do is we're going to prove that A star tree search is optimal if we assume admissibility. And the main reason we prove this, aside from the fact that along the way it's going to prove uniform cost search is optimal, the main reason we do this is because then when we change to graph search, we'll see what part of this proof is the tricky bit we have to get right. All right, so let's think about how tree search works. Right, you start at the top, you maintain a fringe, which is some kind of periphery of some prefix of this tree. And what do we want to show? We want to show that if we've got an admissible heuristic, that's the assumption, and we've got 2 goal nodes, say call them A and B, where A is optimal, meaning it's of least cost, and B is suboptimal, meaning it's not of least cost. What we want to show is that we're going to return A before we return B. In other words, the claim is that the node A will exit the fringe before the node B. Right? As long as that's true, we'll just run until something pops off, and this claim will guarantee us that the first thing off will be a lowest cost goal. So let's prove this in pieces. Okay, so how's the proof going to run? First, we have to imagine the kind of scary scenario. B can't come off before A. Remember, that's bad if B comes off before A. If B is going to come off before A, it's got to be on the fringe. So therefore, B is on the fringe. What else is on the fringe? Some stuff, right? The fringe always looks like this. It contains a bunch of nodes because we've already processed everything above them. All right, B is on the fringe. Is A? Maybe, maybe not, right? But some ancestor n of A is on the fringe. Maybe it's A, maybe it's an ancestor. How do I know some ancestor of A is on the fringe at this point? Well, at the beginning, the start node was on the fringe. When I popped that, the relevant child of the start node was then on the fringe. And if it was popped off, its child is on the fringe. At all points, something on the path from the root to A is going to be on the fringe, maybe A itself. Okay, so this is the condition. It's a race. It's a race between B and this node N, which is an ancestor of A. The claim is that N will be expanded before B. And if that's true, then N's child by the same argument will be expanded before until we finally get to A. So if we can prove this claim, we're done. How do we know N is going to win fighting against B on the fringe here? Well, we have to look at their F scores. All right, first let's look at the F scores of N and A. Remember, N's on the fringe, A isn't, right? But we can still look at their F scores. The claim is that F of N, right, that's cumulative path cost plus admissible heuristic, is less than or equal to F of A. Okay, why is that? Let's dig into that statement. F of N, by definition, is the cumulative cost to get to N, that's this, plus whatever the heuristic says the distance there is, which is less than it actually is. All right, that has to be less than the actual cost to get to A because part of it is shared and part of it has to be an underestimate because of admissibility. So we know that the F cost of N, which includes some optimistic heuristic, is less than the G cost of A. And we know that the G cost of A is the F cost of A because heuristics are 0 at goals. You told me that a couple slides back. What do we know? We now know that F of N is smaller than F of A. Now let's look at A and B. Well, let's look at their costs. And my claim is that F of A is less than F of B. Well, what do we know? We know that G of A, the cost to get to A from the start, is less than G of B, the cost to get to B. That's the assumption. That's what it means that B is suboptimal. It costs more. And since we know that H is 0 at goals, F is the same as G. So F of A is less than F of B. And if we put these together, we now know that F of N is less than F of B, which means N is going to expand before B. So in essence, this is exactly what we want. B, even though it's a goal, it might get on the fringe, but it's going to sit there until every node on the optimal path expands, right? So we can't stop it from getting on the fringe, but we can stop it from coming off. And since we do our goal tests on the way out, that's enough. Okay, that's just putting those things together. All right, that means that all ancestors of A will beat B, and that means A itself will beat B. And therefore, A star tree search here is optimal. And notice in there, we used a couple things. We did use the admissibility of H. Okay, let's look at properties of this thing. Remember we drew these caricatures of how much of the tree you expand? Well, A star and uniform cost both start at the top and work down, like all of them. Intuitively, what A star search should do is there should be directions, like uniform cost search is going to do everything that costs up to the cost of the cheapest goal. But there's going to be some things in here that we can prove can't be on the way to an optimal goal based on the heuristic, and A star search just skips them. So it's going to do the same work as uniform cost search. Erase. It's going to do the same work as uniform cost search, but some of it won't actually happen. It'll do a subset of that work. So this is kind of the caricature. In addition, remember we saw that uniform cost search expands out kind of in all directions. Direction only means something on like a grid or something, but intuitively, even for pancakes, there's a notion of kind of direction intuitively. And uniform cost does everything that's cheap, whether it's making progress or not. A star kind of expands, but in the right direction. So let's look at what this looks like for the Pac-Man grid. All right. So this is what happens. Remember, there's this maze where Greedy went left first, but really you're supposed to go right. And the reason you're going right is tricky is because you actually take a step away from the goal for a bit before you make progress. Uniform cost search will find the optimal path, but by the time it finds a way to get to the dot, it also finds a way to get everywhere else that's of the same distance. And that's like everything but this one square. So it's found all things that you can do instead of just the one you wanted. What does A star search look like? Well, there's some chance this will work. Okay, A star. Here we go. All right, what is A star search? Well, unlike Greedy, right, it doesn't just zip to a goal. And it does, in fact, explore some of this stuff over here to the left that Greedy liked. But at some point it says, okay, based on the heuristic, it's worth taking a few steps in this direction to the right. And it will, in fact, find the right goal. In the process, it does kind of explore some other things. What's it doing up here? Well, based on the heuristic, as far as it knows, there's some kind of wormhole or something. You can maybe get there from here based on the bounds you know. So it does some extra work, but it doesn't do as much as uniform cost. Let's bring uniform cost search back. Okay, so you can see much better. All right, now was it optimal? Yep, looks like it's following the right path. All right. Okay, so A star still hedges its bets, but it focuses more work in the direction of the goal. And the amount that it hedges its bets depends on how kind of optimistic the heuristic is, how close the heuristic is to the actual value. So let's talk about what you do, and then we'll talk about heuristics. So what is this? This is a visualization of some search that goes on in our StarCraft agent, which I will talk about at some point, but not today. But what I will say is that A-star applications are kind of all over the place. One of them is, it's a big thing in video games, kind of finding paths quickly, paths that are kind of sensitive to threats or some other kind of cost. In general, pathing and routing problems use A-star a lot, but also resource planning problems, things like assigning resources to jobs and things like that. Robot motion planning, how you're going to move through some complicated space, that kind of avoiding obstacles. Language analysis, the way you do language interpretation, things like machine translation and speech recognition. There's A-star, something very much like it that uses the same key ideas, is in all of these things. It's all over AI. This idea that you want to be sensitive not just to the cost of what you've already committed to in search, but also the cost of what's to come, so you don't waste time on things that are cheap now but are headed in the wrong direction. Let me show you a demo of the difference it can make. All right, here's a search is not going to start till I press a button. You'll see some action in the console when I start it. Okay, this is like the mastermind Pac-Man. It's not just get to a dot. It is find a way to eat all the dots in the fewest number of steps. Okay, and this involves kind of going back and forth around the board. And what you're going to see, I'm going to press a button, uniform cost search is going to run, and you're going to see the node expansion counts in the bottom. So it's going to go through a lot of nodes because there are a lot of different things you can do before you hit the depth where the solution is. Okay, so this is uninformed uniform cost search here. So let's watch it think. It's thinking 1,000, 2,000, 4, 5, 6, 7, 8, over 9,000 nodes. Okay, so now it goes here, and finally, okay, it got the answer, but it took a while. Okay, 9,000 plus nodes. Let's take a look at what A-star does. Okay, it's not computing yet. You'll see some action in the console. We'll see how long it takes. I'm going to press a button now. Okay, it's done. So much better, 100 to 200 nodes here. So you save a lot of work. And the reason you save a lot of work is because there's all kinds of crazy stuff you can do that the heuristic here, and if you're wondering what heuristics, do your project once. You'll get to design them yourself. The heuristic says, don't do that, that's bad. Okay. Let's see some demos of these before we talk about heuristics in a little more depth. So what demo do I want to show you? I want to show you the same demo we saw before, but now there's more going on in it. Okay. This is a maze, believe it or not. You are getting from green to red. It costs 1 in a light blue square, 3 in a dark blue square, that's deeper water, something like that, and black means unpassable. So this is some kind of boat thing. Okay, so we're going to do a search, and you're going to see white dots appear whenever a state is expanded for the first time. And so let's see what algorithms we can find. So we'll run. Okay. There's something. What was that? Something. Okay, let's watch it again. Okay. They're kind of radiating outward. Do they slow down when they hit the deep water? They actually don't. Okay, let's watch that again. Okay, so they just go straight into the deep water. Oops, I lied to you. I totally lied. Let's run that again. I think I hit something different. Okay, what's that? That's uniform cost search. I mean, sorry. I'm going to go in the corner and reboot now. This is breadth first search. You can tell this is breadth first search because it does not slow down when it hits the deep water. Kind of these diagonal stripes show you that. And look, it finds a path that is kind of a small number of steps but goes straight into the expensive deep water. Okay, let's clear that. Now let's look at what's this. Okay, now it's slowing down when it hits the deep water. Yep, okay. This path looks like it prefers the shallow water. It's longer steps. What do you think that was? Okay, that's uniform cost. Let's look at this. What the heck just happened? Okay. That was actually greedy search. You'll notice it went in one direction and it explored kind of the wrong greedy branch first. I'm happy with my colors. Okay. Let's look. What's this? That's A star. Let's look at what it does. It found an optimal path. It did explore outward in kind of all directions, but it went farther kind of in the directions that made sense, right? Even though like it goes in the exact opposite direction a tiny little bit, that's reasonable, right? The heuristic isn't perfect. Okay, so that's A star search. Same behavior as uniform cost search, but less wasted work. Okay, and what's this? That's depth first search doing its thing. We love you, depth first search. Okay. Oh, depth first search. Okay. All right. So, what have we seen? We've seen A star search works a lot better, and your heuristic saves a lot of work. But how do you get this heuristic upgrade? Okay, we need to figure out for a problem, not just generic, there's no generic recipe. For a specific problem, we're going to walk through some examples of how you create a heuristic, how you know it's admissible, and then we're going to talk about graph search really quickly at the end. Okay, most of the work, as I said, in solving hard search problems optimally is not coding up A star search, because that's you know, you're going to do that once in project 2, you never have to do it again. It's in coming up with heuristics for each problem. Sometimes the heuristics, as we talked about, are solutions to relaxed problems. So for example, if you take Romania and you imagine that in addition to every road you have, you can burrow straight through the earth directly to another city, directly to the goal city, which in this case is Bucharest, well, you know, that is an easier problem. The optimal paths will only be the same or shorter, and they're easy to compute because you do some kind of math on GPS coordinates. You don't have to solve the search problem. We talked about why Manhattan distance on Pac-Man is admissible. Here it's a relaxed problem where Pac-Man can do everything he can normally do plus walk through walls. He's a little bit ghost, okay? And in that problem, you know that you're a Manhattan distance away. Sometimes inadmissible heuristics work fine, but you know you lost your guarantee of optimality, so who knows what's going to happen. But in practice, often a little bit of inadmissibility can make things a lot faster and often work out. You know, no guarantees. Couple examples, and then graph search. Let's talk about the 8 puzzle. How many of you have played with the 8 puzzle or something like it? Yeah, did you like it? Okay, this was like huge a couple centuries ago. It's been eclipsed by other games more recently, but you know, still a fun evening. What does the 8 puzzle look like? Well, it's usually you see it with pictures, but here you imagine there's these numbers, and the goal is to get from whatever scrambled state you're in to this goal state here. So what are the states? Well, they're configurations of this tiley, slidey thing, right? And how would we write them down? Was probably some permutation of integers or something like that, or for a 2-dimensional array with numbers, something. You would encode this in some way. Those are the states. How many states are there for the 8 puzzle? A lot. Okay. A lot. About what? Well, how many choices for the upper left? You know, if you consider the blank to be 9, there's something like 9 factorial or whatever. Actually, it's divided by 2. There's like a whole parallel universe that you can't get to by shuffling. You would have to like break the puzzle to get to the other universe. It's just like French. Okay. So what are the actions available to you? You can move a square into the blank adjacent thing, right? So how many successors does the start state have? How many successors here? 4. So the branching factor is going to be something like 4. What should cost be? Well, like unless it costs more to move the number 8 tile, probably 1. So here the costs aren't that interesting. All right, so let's look at a heuristic. One heuristic is the number of tiles that are out of place. Okay, so from the start state, what is the value of this heuristic? Just stare at it for a second. Like wrong, 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 wrong. Okay, so it's going to be 8, right? I can compute this pretty easily, right? I don't actually have to solve the problem or anything to compute it. So why should this be admissible? Okay, we know that it's 8. Why should it be admissible? We can make an argument, right? We can make kind of an argument that says every time I move a square, maybe I move something from being out of place to being in place. Maybe I don't. But I can't make any more progress than moving one thing into the correct position, right? Assuming I don't count the blank as one of my tiles. So I can make a direct argument, or I can try to argue it based on a relaxed problem. So here you can see uniform cost versus this tiles heuristic, and you can see that if the start state is kind of close to the goal, uniform cost search is fine. You just check everything you can do in 4 steps. There's not that many things. If you're 12 steps away, it makes a big difference if you just try everything of length 12 versus if you try this tiles heuristic that focuses your work. Okay, how could this be a kind of a relaxed problem heuristic? How can I think about this being the solution to a variant of the 8 puzzle that has extra operators? Like what superpower could I give the solution so that 8 is the actual distance?
You have the ability to teleport a tile exactly to where it's supposed to be.
Right, so if you now have teleportation, right, it's cheating, okay, admittedly this is cheating. This isn't your actual solution, but it is an easier problem, and it's easy in this problem to compute how far away you are. All right, maybe we can do better than this. So, for those of you who didn't already read that, how could I do better than number misplaced? Like for example, 7 here is misplaced, but it's kind of badly misplaced, right? So what could I do instead of just adding up the number out of place? What might I do? I could say 7's not just out of place, it's like Manhattan distance from its target out of place. And I could say that for all of them. And this is a heuristic too, right? If you had an easier 8 puzzle where tiles could they were in their own plane and they could slide on their own, well, now you know how to solve it. You move 7 down to its position, then you move 8 over its position. And this is the total Manhattan distance heuristic. You can see that it's admissible either by arguing it from first principles or by reducing it to this easier problem and arguing that this problem, this is the solution to the easier problem. Remember that this start state was 8 away. How far is it now? Well, how far is the 7? That's 1, 2, 3 away, and then 8 is 1, 2 away, and so on. And so I could add all these things up and get that it's now 18 away. That's a big difference for being 8 away versus being 18 away. The true answer is something like, 20-something, and the closer your estimates are, the more focused A star is going to be and the more work you're going to save. So you can see that here, that when you're really far away from the solution, this Manhattan heuristic just saves you a lot of work. Okay, here's an even better heuristic. Why don't we return the actual distance from the goal? Is it admissible? Yes, it is admissible. It is less than or equal to the actual distance of the goal, because it is the actual distance to the goal. Would A star expand a small number of nodes? Yeah, it actually turns out you only expand nodes that are on optimal paths. Great. This is what we should do. What's wrong with this plan? Yeah, like this heuristic requires solving the problem, so you don't actually save any time in the end. Okay, so with A star, there's always this trade-off between getting estimates that are tighter and the amount of work you do per node. You'll see this in your project ones because as your heuristics get more complicated, you start saving nodes, but it actually will eventually start getting slower. And you want to find the right trade-off point. Okay, so you can think about these terrible heuristics that just say you're there wherever you are. There's like you're there, easy to compute, or the things that solve the whole problem. And there's a trade-off here. In fact, you can formalize this trade-off, and you can say essentially that there's some structure to it. So you can have, this will be important for some of the things you want to prove about this, that you can have, say, if you have a heuristic A and a heuristic C, and A is always greater than or equal to C, which one do you want? The bigger one or the smaller one, if they're both admissible? You want A. A is better. So we say A dominates H if it at every state is at least as big, right? Because of this, you can form mathematically what's called a semi-lattice. The point here is, that may or may not be something that's familiar. The point here is that they form some structure. That essentially you at the top have the exact heuristic, nothing's better than that. At the bottom you have the heuristic that just always says 0, which is essentially saying you're at a goal, doesn't even look at the state, you're at a goal, right? And then everything in between forms some structure where some things are better than others, and sometimes like H and B here are just different. They're not really comparable. In general, you can do things like take the maximum, pointwise maximum of two things. That's better than each of the individual ones, though of course it takes longer to compute. The trivial heuristics are the ones at the top and the bottom. The bottom's trivial because it just says 0 and doesn't save any work. The top is trivial because it's kind of involves solving the problem. So this one at the bottom where we always say 0, what do you get when you run A-star search and the heuristic just keeps saying 0? You get uniform cost search, right? Because if you go along adding 0 to your cumulative costs, it's just your cumulative costs. Okay. Let's quickly look at graph search, which is a small change that is going to make everything you build in terms of search algorithms better. The key problem with tree search is you'll notice that you end up repeating a lot of work. Right? Why do you repeat work? Well, because this tree unrolls the graph, and the same bits of the graph show up everywhere. So let's see an example. Here's a state graph on the left. Think about, what does the search tree look like? There's A at the root. How many children does A have? 2. They're both called B. And what's under them? The same thing. So if you unroll this, it's like exponential, redundant, useless work. Right? So you don't want to unroll things, right? It's kind of like, why would you do that, right? Once you've learned what to do with B, you're kind of done. So what we'd like to do is we'd like to have a variant of the search tree that when it gets to B, it says, I've done that. I'm not doing that again. Right? That was bad enough the first time. Okay, so for example, in breadth first search, some of these nodes are not going to be worth expanding. You got to expand S, you got to expand D, you got to expand E, you got to expand P, right? But then as you go through again, you do B and then C, and you get to this E, right? Should you even bother, right? Because you're already working on this elsewhere in the fringe. It's not like there's anything in this subtree that isn't here, because they're identical. So in some sense, once you've got one E, that's good enough. You can skip the other. And there's a bunch of nodes in this tree that you should just skip. Now, of course, there's a good question. Which of these two E's is the one you want? Let's set that aside. If you're only interested in making sure you don't accidentally delete a goal, you can have either. They have the same things, though possibly with different costs. So here it is, graph search in 2 lines. The idea is you should never expand a state twice. How do you do that? You run your tree search. Remember, fringe, things come off the fringe, the children go back on the fringe. You add a set of expanded states called a closed set. It's just a set, and it keeps track of everything you've ever expanded. And before you expand a state, you check to make sure it's not already on the closed list. When you expand something, you put it on the closed list, and if it's already there, you skip it. So you get 1 expansion per state. The second time you're tempted to expand that state, you just don't. So what do you need? You need a data structure that holds the things you've already expanded. It's called a closed set. You implement this with something like a set. Everybody will screw up and call it a closed list. For some reason, it was classically called that. I will screw up. You'll screw up. The GSIs will screw up. Everybody will call it a closed list sooner or later. Please, please, please do not implement this thing as a list. Because what do you do with it? You test membership. You don't want to do that to a list, right? You'll have a bad time. So what you want to do is have a data structure that has constant time membership, and so you want a set. Okay. Can graph search wreck completeness? That is, by refusing to expand a state a second time, could I be unable to find a goal if there is a goal? No, because the first time you expand it unlocks that tree. You don't ever need to look at that tree again if you just want to make sure you can find every kind of state that's reachable. Can it wreck optimality? It can definitely wreck optimality because you got these 2 versions of the state. You want to make sure you get the right one first because it might be the cheaper one. And so optimality now is not just about do you get the best goal, but somehow making sure that everything goes right with the graph search check. So let's really quickly take a look at what can go wrong, look at how to fix it, and then we'll be in a good place to wrap up search. Here's the A-star search. Here's an A-star search graph, right? So here's a problem. Here's heuristics. And let's walk through what happens when we do a tree search. Okay, so S is on the fringe. We pop it. A and B are now on the fringe, and they're competing. And which one are we going to expand first? B. What's the optimal path before we go any further? Is it through A or through B? It's through A, but it's okay, right? A is still there. We expand C. Now we've got A on the fringe and G on the fringe. Which one comes off the fringe first? A, then C, then G. Whew, it worked out fine, right? We were in that scary situation where the bad goal was sitting on the fringe. Okay, it worked out fine because this is in fact an admissible heuristic. Let's see what happens when we have a closed set. So we expand S and we write down closed. Don't do these again, right? We write down S. Then we expand B, which means we write down B. Never expand B again. All right, what do we expand next? C, so we write it down. Never expand C again. Now, what should we do? A. Okay, fine. We write down A, never expand it again. Now, C and G are competing on the fringe. What do we expand next? G. Why not C? C's on our closed list. So somehow we ruined things. We screwed up. We ruined them by expanding the wrong path through C. So we need to make sure that never happens, and admissibility is not enough. Okay, so we need something better. We need something called consistency, and this is the last ingredient for search for us. The main idea about admissibility in general is that estimated things need to be cheaper than real things, right? So in admissibility, the actual cost to the goal, so the heuristic cost, had to be less than the actual cost to the goal. Consistency zooms in a little bit. So in admissibility, here's A, here's some state. H of A, which is the heuristic, might be 4. If there's a goal, essentially it says my hallucinated dream cost to G has to be cheaper than or equal to the actual cost to G, which involves the real costs 1 and 3 here. So this thing here, this is admissible. It's fine. Consistency is something stronger. It says not just for paths to the goal, but for every arc, every action, every arc's heuristic cost has to be cheaper than its real cost. Well, what's the real cost of this arc? 1. What's its heuristic cost? I don't know. What's that even mean? Okay, what does that mean? What it means is we know the real cost of an arc because the graph tells us that. And there's a heuristic on both ends of the arc. And if the heuristic is 4 on one side and 1 on the other side, apparently the heuristic thinks this arc costs 3. That's the difference. And so consistency says the change in the heuristic has to be smaller than the actual cost. And so right here in this example, even though things were admissible, they weren't consistent because the heuristic dropped by 3, whereas the arc only costs 1. So heuristic changes have to be smaller than real changes. So if we made H2, it would be fine. And actually, if you go through that example again with H equals 2, A star search with graph search does the right thing. So here are the consequences. F value on a path won't ever decrease because essentially you go along replacing heuristic costs with real costs. And that means that A star search is going to be optimal. So I think we're going to skip the proof and skip to the summary. The summary is this. The summary is tree search, A star is optimal if you have admissibility. Uniform cost search is a special case with a 0 heuristic. Graph search, A star search is optimal if the heuristic is also consistent. Uniform cost search is still a special case. Consistency implies admissibility, but not the other way around. And in general, when you come up with natural admissible heuristics, they're also going to be consistent. So usually you brainstorm on admissibility, and then you verify consistency. Someone in this class, I promise, will come up with something admissible but not consistent in Project 1, but most of you will not. Most of the things that are admissible will be consistent as well. Okay, so that's it. The summary, A star search uses costs in both directions. It's optimal under the right conditions, and all the work is about designing heuristics. We'll see everybody in section and next week. Oh, I have a small number of account forms if you want them. We've given out hundreds of these, so you shouldn't actually need them, but come up and get one if you want one.